Okay, so I'm going to record lecture 19. And at this point, I think we may want to have a review of what we have learned so far. And then we will move on to study the so-called deep reinforcement learning. So far we have been studying deep learning, and I want to give you a more global picture for what we have learned, because for the past few weeks, we have been studying specific networks and models. So most of this course is focused on the so-called supervised learning. We start from logistic regression, and then we studied trees and ADA boost and XG boost, and then SVM, right? Those are all about predicting YI based on XI. So XI is the input and YI is output, or the so-called class label. And we want to predict YI based on XI. Often YI is either like a continuous or categorical. And in the case of categorical, it is about classification or pattern recognition. But a more fundamental or rigorous formulation is that we want to learn a model P of Y given X, which is a conditional probability of Y given X, where theta denotes all the parameters, for example, the weight and the bias parameters in a neural network. And then a gold standard for objective function is log likelihood. So we want to maximize the log likelihood over theta in order to learn the model. So the log likelihood is a function of theta, and it is computed or defined based on the training data. So suppose we have untraining data, and then we average over these untraining examples for the log for P theta YI given XI. So this log likelihood is a log of the likelihood, which will be the product, right? The product of P of YI given XI, because all those training examples are assumed to be independent. And if you take a log, then product become sum. You can also divide this by n so that you get average log likelihood. So likelihood or log likelihood is a foundation for statistical estimation or inference. So we always formulate our objective function around the log likelihood. In fact, even in GAN, right, we start from the log likelihood for classifier or discriminator. And then we also use this log likelihood as a value function for training the generator. And in VE that we studied last week, we also start from the log likelihood. And because it is intractable, we modify it, we perturb it into a lower bound so that it becomes tractable. And for supervised learning, this is also the case where we want to maximize this log likelihood function over theta. And this log likelihood is average of log of P of YI given XI. So XI, YI, so those are training examples. And we treat this as a function of theta. And we optimize this function. We find the maximum value for log likelihood to get our theta. And this theta supposedly give us the best explanation of the data, so that under the theta, YI has the highest probability given XI, according to this model. Or in other words, this model assigns highest probability to YI given XI. And if we look at the neural network, so X is our input and Y is our output. And we have a neural network so that we transform the input to S, a vector of the same dimensionality as y. So we use S, which is a vector of scores, to predict the vector y. So that's a basic structure. Actually, from this neural network, it directly output S. There's not anything in between. So this neural network is a big box, and often it consists of multiple layers, and each layer it consists of different vectors, so that these vectors, they communicate with each other, passing messages to each other. So eventually, from this neural network, we output. There's now like so there's no gap here. So it just we output a vector S, so that this is considered as a prediction of y. And if we think about this continuous situation where y is continuous, so y can also be a scalar, right? But in general, even for continuous, we may consider the more general situation where y is continuous, it's a continuous vector. So we just use the output S vector to predict this y vector. And then the loss function, the log likelihood, actually can be written in terms of least squares. So that is, if you take negative of the log likelihood, it is a constant plus a least square. So this is 1 over n summation yi minus si squared. So if yi and si are vectors, that will be the Euclidean distance. And often we divide this by 2, so that even when we take derivative, the 2 get cancelled. So in any case, if we look at the derivative of the loss function with respect to si, it is proportional to negative yi minus si. So which is a negative ei, the error for the S example. And then we can use this fact to do this backpropagation. So we can compute, we go back through this network, feed-forward network. So we go backwards, which enable us to compute the derivative of the loss function of the negative log likelihood with respect to theta. And then we can use gradient descent to learn, or gradient, for the loss, it would be gradient descent. For the objective function, it would be gradient ascent. So we use this to learn theta. So that's a basic idea. And in the case of categorical y, so y may belong to, say, 1,000 categories. And you can either just label y as, say, category 1 or category 10, and so on. But you can also denote y by a one-hot vector. So suppose it is 1,000, we have 1,000 categories, then this is 1,000 dimensional vector. And if we observe the kth category, then yk is 1, and all the rest of elements are 0. So now if we look at this part, the top part, then we have S, which is S1 to Sk to Sc, capital C may be 1,000. And here we use a softmax operation to compute P1 to Pk to Pc, again, capital C 1,000. And from this probability distribution, we can either predict Yk by finding the maximum of the probabilities, and we predict this to be 1 or the rest to be 0, or we can just sample from this probability distribution according to those probabilities. Okay, so this Yk in this case is either a category, or in the language model is a word, so a token. So if we have, say, 50,000 tokens, then that amounts to 50,000 categories. So we want to make classification again based on this softmax. So in that case, C, capital C is 50,000, and then we have all those probabilities. Okay, and again, it's computed from this score, this vector of scores, which are often called logit scores. And the softmax is like E of Sk divided by summation of E of Sk, right? So this summation of E of sk is denoted as Z for normalizing constant. And if you take log, it will be sk minus log Z, right? Sk minus log Z. And so we can get sk from this yi. So for the ith example, yi is one hard vector, and si is a vector like this one. And if you compute the inner product, you will see that it will extract the corresponding sk if we observe the case category. So this is the inner product. Okay, so that is this part is just a log of the softmax, where Z is a normalizing constant. And again, you can treat the loss function as a negative log likelihood. And if you do some calculation as you did in your homework, so the derivative with respect to Si will be negative yi one hard vector minus pi, which is a probability vector. So this is just a generic probability vector. For the ith example, you can compute it from this xi, right? Xi as an input, you go through the neural network, it gave Si, S as output. So this is top layer, what happened in the top layer. And again, if you compute the derivative for loss function with respect to Si, you get this negative yi minus pi. Again, we call this negative ei. So, so you have this unified point of view where the negative log likelihood as a loss function, if you take a derivative of the loss function with respect to Si, either for regression situation or for classification situation, you always get negative ei, and this negative ei can be used to do backpropagation by the chain rule, so that from the side chain, you get the derivative of the loss function with respect to theta, and then you can use a gradient descent to learn this theta. And in terms of translation, it is also supervised learning, except that both Xi and Yi are text. So Xi may be an English sentence and Yi may be a Spanish sentence. So we collect, say, millions of pairs, and then we learn to do the translation. So again, here the log likelihood is the same as before, which is the average of log of probability of Yi given Xi. So again, this is a probability distribution, and Xi may be the English sentence and Yi is the Spanish sentence after the translation. And we want to learn this conditional probability, just like in other supervised learning problem. We always use the same notation for the learned model P of Y given X, and we use the same log likelihood. And in particular for this translation problem, so suppose you have a sentence, right, in this order, you have those words or tokens, and T here, T in is a number of input words, and the T out is a number of output words. So the idea is that in the transformer, you have encoder. So this encoder output for each word a vector. Okay. But this encoder has this self-attention mechanism, so that the vectors pay attention to each other and collect message from each other. So after a number of rounds, then we observe or we produce those vectors that are contextualized. So essentially, each vector contains information about the whole sentence from the perspective of this vector. And then you use those vectors generated by the encoder as input to the decoder. Okay, and then from the decoder, you then decode the Spanish word one by one, starting from the special symbol of start, and you generate the first word, and given the first word, you generate second word and nth word. But you always condition the input vectors until you generate the end of sentence, and then you stop. Okay, so here we can write the probability. We learn this probability of Y given X, right? For each training example, P of Yi given Xi should be the product t from 1 to t out, right? And p of yit, and then y of I. So here, this should be comma, I comma, and less than t. So here, less than t means that all the previous words that you have generated. So p of I comma less than t. Okay, and you also condition xi, the input, the input English sentence. Okay, so this sometimes called auto-regressive model. That is, each yit is predicted based on the previously generated words, and also xi, the input. So this is objective function, and again we optimize or maximize this log likelihood. Okay, we take log, and then we get the log likelihood, which is summation, right? Log of this one, and each one you see, you're predicting a word. So this is a classification problem, as we mentioned in the previous page, so that you can use again this softmax, right, to get this probability, and then you get this error by propagation. So it's essentially the same as a classification. So here we have been talking about the so-called supervised learning, where you have input and output. But in the case of unsupervised learning, for example, you only see a lot of images, say images of faces. And in that case, we can still use maximum likelihood. So here, our purpose is to learn the probability of xi. So that is, we learn a probability distribution or probability density function of x with a parameter theta. So this is p theta x, so that this probability assign this density function assign high probability density to the observed examples. So, or in other words, we want to learn this p theta x to approximate the underlying probability density function that generates the data. So this is the so-called density estimation problem. Unlike in the supervised learning, where we learn the probability of yi given xi, here we just learn the probability of xi and parameterized by a parameter theta based on some neural networks. And here we still want to maximize the log likelihood, which is the average of log p theta xi. Sometimes this p theta x may not be tractable, or there's some so-called intractable normalizing constant. In that case, then we can do something to perturb the probability of the log likelihood and to make it tractable, for example, in the variational autoencoder. So in the case of language, actually, if I just give you a lot of English text, you may also consider this as a unsupervised learning problem, and you still want to learn this probability for the observed text. So for each training example, then you can model this by a autoregressive model, so that you predict the next word given all the previous words. So that can also fit into this framework of unsupervised learning. Although those texts are actually generated by human, right, with knowledge and also the skills of logical reasoning and learning and planning. Therefore, it is hard to say it is unsupervised. For example, when a baby grows up, she may see a lot of images, unlimited amount of images, right? It's readily available, but she may not receive unlimited like a language input. So the language input is like a supervision given by other humans. So there may not be such big data. So therefore, for the language processing, it may be necessary to figure out the underlying logical rules. But for the transformer model, if you can predict the next word based on the previous words, you probably need to learn all the knowledge and the reasoning and the learning and planning skills for human being. So that is, if you really train what I call super pirate, as good as a oracle, for example, it may possess a lot of knowledge and skills already. But then often you need very big data in order to achieve that. However, for a human baby, as I said, she may have unlimited access to the image data, but she only has limited access for language data. So in that case, maybe a simpler model with more precise rules should be necessary. But that's still a unsolved problem. So currently people still trying to scale up the transformer model to see what type of skills that you can learn. For example, the current transformer model, such as GPT-3 or Flamingo, can do few shot learning. So that is, you show some demonstrations and then you ask a question, it will give you the answer. For example, you show some demonstrations for correcting the wrong spelling of the words, and then you gave the GPT-3 the a wrong spelled word, and GPT-3 can actually correct it, generate the correct spelling. So this may appear to be like a GPT-3 can learn just from a few examples in the online manner, right, without changing the model. But it may also be the case that the GPT-3 has seen a lot of training examples. For example, this spelling correction examples together, right? And then you see this like a pattern. So what GPT-3 does may be more like filling in the answer so that they form a very coherent pattern with the same statistical regularities that you have seen in the training data. So it is really about modeling this probability distribution and how simple your model is. So this is unsupervised learning, but for supervised learning, of course, it models the conditional probability distribution. So the point is that in those formulation, we always want to learn either the conditional probability distribution or marginal or unconditional probability distribution. And then if we take a log for this probability distribution, we get the log likelihood as a function for the parameters, and then we can maximize the log likelihood. So this is a current framework. In fact, we can trace this framework or paradigm back to Gauss. So he developed least square method, and he justified this least square method by assuming the Gaussian distribution, which bear his name, right? And then the maximum likelihood, or the so-called maximum a posterior, then lead to the least square estimate or least square loss function. Okay. For the past few weeks, we have been studying this neural network. I mentioned that we have the input, right? And then you have neural network give you the embedding, or eventually give you this S vector, the vector of the scores, which is used for predict Y. And for this neural network, so the current paradigm, which may, especially for transformer, which may represent a paradigm shift, is that we treat the neural network as a team of vectors. That's our perspective. So instead of seeing things in terms of channels, feature maps, we see them as a team of vectors with multiple layers, and those vectors then talk to each other, pass on the message to each other. So each vector is called an embedding. And in the language, you can embed each word, right, as a vector, and those vectors then talk to each other and collect information from each other. So this embedding point of view is extremely important, a very important lesson from the deep learning. So of course, the original license for neural network is that with say the sigmoid rectification, right? We get a piecewise constant approximation to a nonlinear function, and with ReLU rectification, we get a piecewise linear approximation to a nonlinear function. So this is from a function approximation point of view. It's a very effective, flexible function approximator. So this is original point of view. Based on that, then the modern point of view is that we have a team of vectors or embeddings, and then they represent different things and become, say, more and more abstract. For example, in this supervised learning, right? So embedding, as you get closer to y, it is more about y than about x. So about it is more and more abstract. And we can also, as I mentioned before, we can also see neural network, convolutional neural network as a team of vectors instead of channels and feature maps. So you have multiple layers for vectors, and vectors at a higher layer are compositions, spatial compositions for vectors at the lower layer. So they are of higher dimension. And eventually you get a single vector, and then you make the prediction. As you go up, then this vector are more about the class label than the input example itself. So it becomes more and more abstract in that sense. And for the transformer, at each layer we have vectors, each vector for each word, right? And each vector then pay attention to each other. We have this so-called attention map, which is a softmax probability in the form of softmax probability. And we use this attention map to average the, to get a weighted average of the value that extracted from other vectors, including itself. And then we update this vector, right? So at each layer we do that. And also later, what follows is that each vector then think for itself by a multi-layer perceptron or feed forward neural network, and also with a layer normalization type of transformation. So each layer can be considered as one round of update of this vector, and with multiple layers, say 64 layers, you do 64 rounds of update. So that's the basic idea. Again, it is based on a team of vectors. And here, each vector corresponds to a word, right? But you can also include some other vectors, freelancing vectors. So they can also contextualize with other vectors, and then they collect the information. And you can also use those vectors for some purposes for like predicting something. And you can also arrange the vectors in different layers. So those are the current point of view for neural network, including graph neural network, where each node on the graph is represented or embedded as a vector, and then those vectors pass message along the edges for the graph. Okay, that's the neural network, different type of neural network. And this is one lesson, right? The embedding. So in neural networks, you see multiple layers of embedding. Another lesson is that, for example, in this transformer, right? So you can think of each layer as a round for updating. So they each vector collect information from other vectors. So it's like a round of meeting. So, and then they talk to each other and update their own source vector. And if you have 64 layers, it is like 64 rounds of computation. So this can be considered as another lesson, which is learned computation. So that is you actually learn a iterative algorithm. So this 64 layer of transformer may be considered as 64 steps of iterative algorithm of keep updating those vectors. Okay, so that is instead of think of this as a multiple layers, you may think of it as multiple steps. So these 2 point of views are actually almost exchangeable. And even for convolutional neural network, at each layer, before pass to the next layer, you may allow each layer to do several rounds of updating, right? So this is like a recurrent or residual type of updating. And you can learn this updating as an iterative algorithm and then pass to the next layer and so on. So that is, you do some recursive or recurrent or iterative computations. And you don't have to know what type of function this recursive or iterative computation trying to maximize. So you just learn this iterative algorithm and embed this iterative algorithm into a classifier or whatever objective function. And then you can use a backpropagation to learn this iterative computation. So this is the idea of learned computation. So you don't have to learn an objective function and then design an algorithm. You just learn this algorithm as a part of the model. So this idea of learned computation is also a very important point of view. Even in this VE, you can consider this Q, the inference model, as a learned computation for sampling from the posterior distribution, the true posterior distribution. Okay, so this is the 2 point of view, which are certainly related, right? Because if you have embedding, you always want to update those embeddings, or compute those embeddings, and then you can just learn an algorithm for computing and updating those embeddings. And then the neural language is that with this continuous embeddings, you can then the computation can be in the form of continuous differentiable operations. For example, you can multiply a vector by a matrix to transform it into another vector. And this vector may be either considered as a transformation of this vector or extracting some information from this vector, say query key and values. And you can also look at the inner product. For example, this may be a query vector, this may be a key vector, right? And you can also use this element-wise product. This may be a vector of gates, and this may be the vector of the values you want to control. Yeah, so this, you can think of this as a neural language, and also you can impose element-wise nonlinear transformation, for example, ReLU. So those are the things you can do. And then you can learn the embedding and also the computation for updating the embedding. So everything is done in this black box by the differentiable operations on the vectors. And then you can learn the underlying matrix representing the operations. And so you only need to take care of the input and output. Say the input may be a sequence of words, and then the output may also be a sequence of words. And then you can train the model, the so-called end-to-end. So you only need to maximize this log likelihood, and then all the parameters in this big box can be learned. Okay, so that's the basic idea. I think with this review, we are ready to study the so-called deep reinforcement learning. And this is actually a very big and complex topic. So for this course, I think for the sake of efficiency, I think maybe we can start from AlphaGo so that everything is concrete. So instead of starting the formulation, like a Markov decision process, this abstract formulation, I think a concrete example is a much better way for learning this subject. So AlphaGo, everybody knows that AlphaGo beat the top human players a few years ago, right? So this playing the game. So the game is actually very complex. So it was surprised at that time that actually the AI can play the game so well. So I'm going to give you a brief introduction to this AlphaGo. So Go is a rather ancient game, a board game. So I think it exists maybe for 1,000 years. I don't know the exact history in China, and then later it became very popular in Japan, where you have the professional players from level 1 to level 9. So level 9 is the top level, and then they play in different tournaments, very prestigious. And these days, in the three countries, China and South Korea and Japan, there are many good players, top players. So the idea of the Go is that you have two players. One player use a black stone, always play first. The black player always start the game, and then you have the white stone for another player. For example, the black player plays stone here, and white player plays stone here, and then black and white and black and white. So so the point is that if, for example, this become a black, then this white stone will be encircled, right? So it will be like a takeout, and then you continue to play. So in the end, when there's no more place, you can play the stone, and then you just count. So who's count the number of stones or something like that, and then you decide who wins the game. So here we use Z to denote the result, the score. So from the black player's perspective, so it's like a reward or score for Z. So Z equals 1 if black wins, -1 if white wins, and 0 if it is a draw. But you can also count how many stones are the difference, right? And the board is can be of different sizes, but I think now people mainly use 19 by 19, so that there's a balance between whether you occupy the corners or whether you occupy the inner part. Yeah, so that's the basic idea for this game. And so you can think of a game tree. So the game tree is like you start from the blank, right? Blank board. And then if it is the turn of black player, so the black player can place the black stone in different positions. So each position corresponds to an action. Okay, and each action lead you to a new state. Okay, so that's called the state. We use S to denote state. Okay, and then it is white player's turn, and then again the white player may place white stone at different positions. For example, starting from here, where the black player has a stone here, and then the white player can place white stone in different positions. Again, each position selected by the white player is action of the white player, and we use A to denote the action. Okay, and you can keep play until the end. So in the end, you decide whether the black player wins the game or not. So if the case is 1, otherwise it will be -1 or 0. Okay, so that's a game tree. And for a tree, we often care about how broad it is and how deep it is. So for the Go, the game tree is really big. It is both very broad, very big breadth, and also very big depths, very deep. You need to play a lot of lot of steps until the end. And at each step, especially at the beginning, you have a lot of different choices for placing your next stone. So it is also very wide, this tree. Therefore, the tree is just too big. So if it is a small size, you can actually solve this game by finding the minimax solution. So that is at each step, you want to maximize the reward Z, average Z for the black player, and you want to minimize the C for the white player, and you're just doing min-max, and then you can get those branches that that optimal, that is satisfied as a min-max, and that's the solution for the game. But unfortunately for Go, this tree is too big for exhaustive search. It is impossible. So therefore, you can only search the more promising or reasonable moves or actions, and then search those branches that are very likely. And you use some random Monte Carlo type of method. So this is called Monte Carlo tree search method. But then in order to do Monte Carlo tree search efficiently, you need to learn some deep learning models to help you to do the search. So in today's lecture, for the rest of this lecture, I'm going to talk about how to learn the deep learning models for doing this, for which will be eventually used for helping us to do this Monte Carlo tree search. So first, for state S, we can denote a state by 3 19 by 19 images. They are not really the real images, but you can think of this as images. So the first one, the first image is a binary. So where 1 indicates that there's a black stone. And for the second image is opposite. So if there's 1, then it indicates there's a white stone. Okay. So therefore, for the position, if this is 1, then the same position cannot be 1 for this second channel, right? But if this is 0, which means there's no black stone, it may still be 0 here, which means there's no white stone either. It's empty. And the third channel is like all 0 or all 1. If it is black turn, it will be all 0 or all 1. If it is white turn, it will be all 0. So that's enough for us to represent the current state of the board. So S can be considered as a 3-channel image, 19 by 19 image. And then for the action A, so given the current state, you just place your stone in a certain position. So supposedly, because this is 19 by 19, right? So there are 19 by 19 choices where you place your stone. And you also add 1 for the pass, which means you do nothing. And then you let your opponent to do the next move. So you can think of this as 19 by 19 plus 1 categories. Okay, so, and then we have the following 2 things that we want to learn. So they are commonly used in reinforcement learning. One is a policy, which is a probability of action given state. Because action, we only have a finite number of actions. So you can think of this as a classification problem. So given the state was the underlying category of action. So you learn a classification network. But it is in the form of conditional probability. It is often not deterministic because especially in the beginning stage, right? So for a state S, there may be many different choices following a certain probability distribution. Okay, so we model this policy often as a stochastic policy in the form of a conditional probability distribution or a classification network. And then we also have value. So there are 2 types of values. One is the state value. We denote this as V of S, the value of S. So which means if you play according to a certain policy defined here, and then play to the end, starting from this state S, then you may have different trajectories because the policy is stochastic. So, and then for each trajectory until the end, you get the Z, and then you average the Z. So that's the average. E stands for average of Z given S according to a certain policy. And this is the value. So which means whether this state is desirable to the black player or desirable to the white player. If the value, for example, is 0.7, it is very desirable to the black player, right? So this value is another aspect, so complementary actually to the policy. And you can also have the so-called state action pair value. So this often denoted as Q function, QSA. And QSA means that you start from this S, and then you take this action A, not necessarily according to the current policy, but for the rest, you play out this policy, and then you get your final result, Z, and you average those final scores. So that's an expectation of policy of Z given S and A. So here A can be any A. It doesn't need to follow any known policy. So because here we condition on S and A, both S and A. So it's a state of state and action. So this measures the value of this action A at the state S. So this is the Q function. And we have these two types of values. Of course, they are related to each other. Okay, so and then we want to learn the policy or value. Actually, after learning the policy and value, we can already play the game. For example, if we learn the policy, if it is really good, then at each state, we just sample A from this state, or just use A with the maximum probability, and then we play out this A. So, or in the value, if you know this this value QSA, and then at each state S, you just find A that maximizes Q function. So that will be the most valuable move, right? Or in other words, if you use VS, the state value, then you want to choose A at this state, AS. You choose A that leads to the next state, say S prime, with the highest value. You can also do that. So that is knowing the policy or value, you can already play the game. And you can either learn the policy or learn value. So when you just learn a policy, it's called policy-based learning. If you just want to learn value, it's a value-based learning. But oftentimes, people learn policy and value together because that actually, they help each other. They complement each other. Okay, so for the sake of concreteness, so let's look at how AlphaGo learns the policy and value. Okay, so let me go next. So AlphaGo parameterize this policy and value. So policy and value based on a network. So there's a neural network which is a body that is shared by both value model and the policy model. And this neural network can be a CNN or which implemented as a resonate. It can also be a transformer. I'm not aware of anybody has already done this transformer, but I assume that it can be very, very powerful. So you can learn very good policy and value. But even the resonate can already do very well. And then you can go through two different heights. Both are like multi-layer perceptron, but maybe only a small number of layers until, say, for the value network, you just output the predicted value. So this is scalar. But for the policy network, you have 19 times 19 plus 1 possible actions corresponding to those positions that you can place your stone or just a pass. And so this is a conditional probability for classification. So you can just use the second height to generate the softmax probabilities for those actions. And this gives you this policy. Okay, so this is a neural network. It is really more about our, I would call our emotions. For example, this VS tell us how desirable this state S is. Okay, and this P of A given S is more like a reflex or impulse. So given at this state, you use network quickly generate a action. You want to do something. You want to take certain action. Okay. For example, people have this emotion of anger or fear, right? So those can trigger those policies so that you can fight or flight, this type of things, or something that you keep doing practice, and eventually it become your muscle memory. For example, swimming or riding bicycle or walking even. So those are based on the practice. You just learn this so that you can do it without much of thinking. Okay. Desire, and here this impulse reflects this type of things. So it's more like a feeling or an emotion. So without too much for conscious thinking. So you learn this too, as I mentioned, use either one, you can already play the game. Okay, so how do we go about to learn this neural network that generate policy and value? So we can do this in several steps. So in the first step, we do supervised learning. We learn from human players. And in AlphaGo 0, they actually remove this step. But for the purpose of teaching reinforcement learning, I think it is better to start from AlphaGo, the original version, where you learn from the human place. You just collect a lot of like pairs. This is state, this action, and then you learn a conditional probability of A given S as a policy, and you write this sigma to denote all the parameters in this neural network, and the sigma stands for supervised. So as I said in the beginning of this class, so for supervised learning, we just need to maximize the average of the log likelihood. So AI given SI. Okay, so AI is almost like our Y, and SI is like our X. So it's still a classification, so input and output. So here we try to mimic how human play the game. So it is essentially a imitation or behavior cloning. And then we want to maximize this log likelihood. We can do this by stochastic gradient descent. So that is at each step, we either take one example or a small mini batch, and then we take a derivative, and then we update sigma by moving according to this derivative or gradient, so that we do gradient ascent in order to increase this log likelihood or increase the probabilities for the actions that given by human beings. So this is just supervised learning, as we mentioned before. And after you learn this network, you can do reinforcement learning to further strengthen this network to make it stronger. Because this policy just learned from those human players, who are not necessarily that like a top professional players, because we don't have a lot of data for those players. So we just look at those online play for those average, probably amateur players, right? So therefore, you do not expect to learn a very strong policy. And also there's some inherent shortcomings of this type of learning. So you learn this, you just mimic this behavior, human behavior. But there's a danger of like a shift. So that is, if you play out this policy, and then eventually you may get to a certain state that you haven't seen in this training data, or you cannot find any similar state in the training data, so that the generated action may be far off. So therefore, you can go off track if you're playing out this this policy learned by this learned from human. So imitation learning is not really a good way to learn a strong policy. because, as I mentioned, there's a drift issue, and also you are not directly optimizing the outcome of this policy. So you don't really know how things will play out. So therefore, we want to learn another neural network, the P of rho of A given S. So this is another policy model where rho stands for reinforcement. So that's RL stands for reinforcement learning. So you can initialize this rho from this sigma, that is the network trained by supervised learning. And then you let the rho to be the black player to play against the sigma as a white player. Say at this S, right, the black player, you according P rho, you get A, and then you get to another state, and then you let sigma play as a white player and keep playing out until the end, and then you get the Z, the result. And then what you want is for this A, if A give you a good result, positive one, you want to increase the probability of A given S. But if this A result in a loss, so Z is negative one, you want to decrease the probability of this A. So therefore, we learn this rho, which denote the parameters of this reinforcement learning policy network. So we update the rho by still the derivative of log P rho A given S, but we multiply this by Z. So Z can be positive one or negative one or zero. So as I mentioned, if it is positive one, that means this action A is good. You want to increase its probability by gradient ascent. But if Z is negative one, that means the result is bad. So you want to decrease the bad action that lead to a bad result by gradient descent. Okay, so therefore you multiply this by Z. And if you compare this with the supervised learning algorithm, you see that you hear this A is generated by human, is given by human. But here, this A is generated by the current P rho, which is yourself. Okay, so that's the difference. So here you always want to find sigma, improve sigma, update sigma to increase the probability of human action, because human, you treat the human action as your teacher and you try to increase the probability. You always consider human action to be good. But here, this A is your self action and you don't know whether it's good or not. So you can only wait until the end of the game to know whether it's good or not. So if it is good, it's positive one. It is as if you learn from the human, right? So you increase this probability. But then on the other side, if it is negative one, you have loss, right? You want to decrease the probability of this bad action. So therefore, there are two differences between supervised learning and reinforcement learning. So in supervised learning, so you have this derivative where there's AI is generated by human, but here this AI generated by yourself, the current policy. And also in supervised learning, there's now Z, but here in reinforcement learning, you have the Z plays the role of reinforcement. So this algorithm is called a policy gradient, so that we can keep updating the policy so that it generates better and better actions, because we, based on the result, we increase the probability of good actions and we decrease the probabilities of bad actions. So that's the reinforcement learning. And after reinforcement learning, you can then learn the value network. So that is, you let the P rho, after you train by reinforcement learning, you let the P rho to play with itself. Okay, let P rho to play with itself, so that you keep, say, as SI, you use the P rho to generate A, and then you get to the next state S prime, and you continue to use P rho to generate A prime and keep going until you get the end, you get ZI, right? And then you want to learn this value network with theta SI to predict ZI based on this least square loss. So you want to minimize this least square loss. So therefore, you want to update theta, which denotes the parameters of this value network, by minimizing or gradient descent on the least square loss, so that at each state S, right, you can then predict the result Zi. And you not only do this for this Si, but you can also do this for S prime here, and also for future S. Okay, for you to do the to make the prediction. But the point is that if you get closer, as you get closer and closer to the end, supposedly your prediction should be more and more accurate because of the there's many different trajectories, right? A lot of fluctuation. But if you get close to the end, then you don't have many possible trajectories. So you can be more certain about this GI. So this actually is also a rationale for search, which means you look ahead, you play out the actions and look ahead so that even though you may not get to the very end to get the GI, you may still get this V theta, so that the V theta that closer to the end may give you a more accurate estimate for this GI. Okay, so that is we use 3 steps to learn a supervised policy and reinforcement learning policy by policy gradient, as I mentioned before, and also this value network. So with either policy network or value network, you can already play the game, but still it is not good enough, and you need to use Monte Carlo tree search to further look ahead, to think it over, and then pick your action. So I will discuss Monte Carlo tree search in the next lecture.